Okay, this is lecture 19 for interconnect, and we go to the review of our previous lecture, lecture 18. So at the beginning of our lecture 18, I told you that nowadays backside power delivery network, so we sometimes make it short as backside PDN. But anyway, this is a new way to further scale down a transistor. Actually not a transistor, but combination of transistors can be reduced. Its size can be reduced by adopting this backside power delivery network. So after that, we have thought about wires, and we need several metal wires. Several means that around 10 or even larger number of metal layers are used. It can be modeled as a distributed RC network. So if we have a certain metal wire, so we wanted to send our signal from source to destination, and in this case we can divide it into several pieces. So how many? So infinitely large in ideal case. Then we can thought about the infinitesimal length scale for this segment, and each segment can be represented with its resistance component and capacitance component. So in the previous lecture 18, we have thought about mainly the resistance part of our wire. So sheet resistance was introduced. So from the viewpoint of a designer, so what they can do is like this. From the top view, they can see this length and this width of metal wire. So depending on the technology, they have the minimum length and minimum width, but increasing it with multiple of this minimum length and width is up to designers. So they can increase the length and they can increase the width. However, one thing they cannot change in this technology is the thickness of this metal wire, because this quantity is given by the technology. So in this sheet resistance, they just introduce this kind of constellation. So this is the bulk resistance, and this is the thickness of our metal wire. So if the thickness is large, for example, if our technology guys provide this kind of tall wire line, then yes, we will have, for given area, given unit square, we will have smaller sheet resistance. Instead of that, on the other hand, if our technology guys just provide very short metal wire, then obviously due to the reduction of cross section, we will have a much larger value of our sheet resistance. That was the main content of our previous lecture. So today we will continue this kind of consideration. So first consider resistance, after that we will move to the capacitance. Let's go to this part. Well, this third slide in this interconnect modeling just shows the material selection. Actually, as a designer, we don't have any freedom to select the material, but technology has evolved to adopt the copper. So previously the aluminum was used. So aluminum has many good properties. Actually, it is, first of all, it is cheap and it is easy to handle, and it has a good relation with our silicon material. So previously, aluminum was used everywhere, almost everywhere. I mean that not only this metal wire, but also the gate metal was also used with aluminum. However, after that, they have found that aluminum has a certain bulk resistivity given by this number, and maybe we can find better numbers for other materials. But you can find that actually silver or gold, they have lower bulk resistivity, but they are noble metals. So if we adopt this kind of a material into the mass production, then maybe we need a higher cost for fabricating, material cost for fabricating a given capability. So instead of that, we have copper, and copper has still lower resistivity. It has comparable resistivity with silver and even lower than gold. That sounds good. It is cheap and we can find many copper materials so easily. So it seems to be good, but there was a critical problem with this copper. So when copper is just inside the silicon, copper inside the silicon just contribute a deep trap level. Simply speaking, if we have copper inside the silicon, then our leakage current is increased drastically. So it is actually a contamination. So this copper is one of the representative cause of contamination. So there was a certain taboo about using copper in the silicon technology for a long time. So although copper has good properties from the viewpoint of resistivity, but they never tried to incorporate copper into the silicon material, the silicon technology. However, time has elapsed and there was a certain pressure to find out even better material than aluminum. So what they found is so-called dual damascene process. So although here we have something, but here you can see that starting from this one structure, eventually we wanted to make this kind of structure. So can I just magnify for your interest? Okay, so as you can see here, let's assume that we have already made a certain lower level wire. So lower level, M1 level shown here, and eventually we wanted to introduce the next level like M level M. Then how can we make this new level on top of already fabricated lower level? So simply we can make this kind of thing. We wanted to make this kind of thing. Here we have a certain level, and oh, so sorry about that. This is M1, this is M2, whatever. So this is a lower level and this is a higher level, and we wanted to make this kind of a structure. Then how can we do that? Depending on the procedure, we can find one path or another path. This is called as via first, and this one is called as trench first. It is because this kind of structure is called as via, and this kind of structure is called as a trench. So in this trench first, we first make a trench. After that, we introduce BR. But anyway, the final form looks like this. Here we have a structure fabricated by twice processing, this one. After that, the important point is not this shape itself, but please have a look at this is a locate material, but here we introduce something. Something means that here, before filling the copper into it, but we wanted to introduce, please have metal barrier. So barrier metal is introduced. It is used to prevent our copper atoms inside this metal part escape from that position, because copper is quite a good immigrant into everywhere. So if we don't introduce this kind of specialized material, barrier metal, it will propagate or diffuse over our chip. So eventually when it touch into our silicon material, then it will become a contamination source. So we introduce well, again pencil is stuck, but let's wait for a while. Okay, so with this barrier metal, we can prevent the diffusion of copper. So that is our way to make copper wire. So that was really a big breakthrough when we developed a newer technology. Previously we used aluminum, but it has moved to this copper. It has been occurred around 130 nanometer technology at the time. They changed it into copper. And what about nowadays? We are now living the November of 2023, and now we feel that even this copper is not sufficient to provide sufficiently good conductivity for our wires. So there are many researches to introduce another new material to make this wire. So, however, there is no clear answer to that. So some research institute suggest, for example, IDM or IMAC suggested to use certain material called ruthenium, but this is also kind of very rare material, so I'm not quite sure we can afford it. Anyway, this is using the copper is nowadays a standard way. So now let's go to this one. Up to now we have thought about resistance part, R part, and now we have to consider capacitance part. But before talking about our capacitance, let me just consider about this yellow one. You see here we have a certain yellow material. What is it? This is the material filling between one metal and another metal. For example, if we have one metal wire line, and if we have another wire line, then what will happen? Since we have one metal and another metal, so what we can say is between them we can think about the electric field. For example, let's say that we have applied the 0 volt to this left wire, and let's say that we have applied a positive voltage to right metal wire. Then what will happen? Here, since we have a higher voltage and lower voltage, so we will have a certain electric field line like this. So simply speaking, these two metal wires also introduce certain capacitance to our system. This is the origin of capacitance we are considering right now. But my point is in this slide is then which material is used to fill the gap between this one metal wire and another metal wire. What will be the best material we can consider in this case? If we wanted to reduce the capacitance, so point is we wanted to reduce the capacitance, not increase the capacitance. This is somewhat different from the gate oxide. So do you remember? So previously when we had MOS step, so here we wanted to have a certain oxide layer and we wanted to increase the capacitance. There was a question by a student why we have to maximize this C-ox. It is because for given gate voltage, we wanted to maximize the number of inversion charge as much as possible because we wanted to maximize our drain current level. So that was a common way. So instead of increasing the voltage, so V corresponding to VDD, by increasing the oxide capacitance, we can increase the drain current. That was the situation. However, although here we have once again capacitance, but this capacitance is not a good capacitance from a viewpoint of engineers. We wanted to send a certain signal from here to there. However, if we have a strong electrical coupling, then the signal propagation will be delayed by this additional capacitance. Because, you know, if we just increase the voltage, then this voltage is increased. However, when this voltage is increased, and if we have a strong capacitive coupling, then we must also increase this part. So this is not a good case for fast propagation of our signal. So in this case, we must reduce the capacitance. So please think about our case. For our gate oxide, what we did was introduction of a high K material. Sometimes people just write down K or kappa anyway. So in this case, then what is our natural consequence? If we wanted to reduce the capacitance between these two metal lines, then our choice should be low kappa or low K material, which has lower relative permittivity, so to reduce the capacitance coupling. Okay, so maybe you have already heard about this kind of story. Then I just briefly mention how can we introduce this low K material. So low K material, here the criterion low or high is always silicon dioxide. because this is the most frequently and most easily available material. So in the case of gate oxide, we have to introduce certain material like hafnium oxide, and this one introduces higher kappa value over relative permittivity. And in the case of silicon dioxide, in the case of low K material, what we do is, for example, introduction of fluorine atoms into this silicon dioxide. Then it can reduce certain amount of capacitance. Or sometimes people has used like this kind of material, introducing copper and hydrogen. Then it is experimentally verified that we have a reduced value of copper. And another type of approach is just to use silicon dioxide. However, instead of densely packed silicon dioxide, make a silicon dioxide layer having many pores. So, yes, this is silicon dioxide. However, inside it, we have some pores. So, inside it, we don't have any material. Then what will happen? This is corresponding to just air, and air. Then what is the relative permittivity of air? Epsilon over air is just 1, very close to 1. So the lowest value we can imagine for ordinary material. So therefore, simply by introducing certain pores into our silicon dioxide layer, although this part we have just silicon dioxide, silicon dioxide, silicon dioxide. However, some part we have pores, so we can reduce the relative permittivity. So nowadays, the achievable value of relative permittivity is about 2 point something. So compared with our starting value like 3.9 for silicon dioxide, it is corresponding almost 2 times reduction of our relative permittivity. So that is used, and people are still trying to introduce another and another new materials into this low K part. So now let's come back. We are now talking about the same thing. I have already explained it in it, so we can just quickly move to the next part. So wire not only introduce resistance but also introduce capacitance. So now since that this is our central wire, then it has many other layers. For example, this is the same layer. We have neighboring wires, and also we can have another and another top or bottom layer. Of course, you may say that, oh, how can we connect this layer n plus 1 and layer n? Or how can we connect layer n and layer n minus 1? However, that happens, connecting these layers happens in a short or relatively small part. I mean that here we have one metal wire running in, for example, n plus 1 level, and we have another metal wire running in n level. And so for certain position we can find a via. Yes, now we have a via. So this is n plus 1 layer and n layer. Of course, for this part they are connected. However, this is only for small amount of area and for most of our metal wires. This and that different layers are just separated when we make the cross section. So of course a low-K material is just filling this gap. Then what is, when we consider small portion of our n plus 1 layer and another small portion of our nth layer, then what is the capacitance? Of course, we can consider the distance between them and the relative permittivity of the filling material, low K material. So now let's come back once again to this central metal wire. Then if we have this kind of configuration, I mean that here layer N we have several running wires, and we assume that n plus 1 layer, top layer and bottom layer are just given by very wide metal plate. In this case, we can see that the intra-layer capacitance can be obtained by this way. In the same layer, the phase is given by T and distance given by the spacing. So this is one factor. So distance is given by the spacing between two wires, and the area of facing planes are given by the thickness of our metal wire. On the other hand, please have a look at the opposite case. On the other hand, if we consider this n and n plus 1 interconnection, then in this case we have to say that this width is corresponding to the phase, and distance between nth layer and n plus 1th layer, that is given as the distance. So are you all with me? So now this is corresponding to the factor for our this capacitance, and this is corresponding to this capacitance and this capacitance. Once we assume that the distance between each layer or this distance between layers is the same as just h. I mean that here although we have introduced h1 and h2, we have assumed that h1, h2 are the same to the h. Then we can find that the total capacitance originated from these surrounding metal lines can be simply obtained by this one. Why we have it twice? Yes, it is because we have top and bottom. Why we have two? Okay, because we have left and right. Of course, if we don't have this pattern, yes, that's possible, then we will not have this number 2. And if we don't have this one, then we will not have this horizontal contribution any longer. So if you have just a very lonely line without having any neighboring metal wires, then capacitance will be quite small. But what we wanted to calculate is the worst case capacitance, the highest capacitance we can expect for given technology, and it can be written as this form. It is obvious that in order to reduce this capacitance, so we must increase this height. Yes, this and that can be increased. Then we can reduce the vertical capacitance. Then what is the problem of this strategy? if you introduce layer 1 and layer 2 here, so layer n and layer n plus 1 here, quite much separated, then we can effectively reduce the capacitance. Then on the other hand, the BR between these two layers will introduce significantly larger resistance. That is not a good sign. So although you can reduce the capacitance by separating them, separated layers, then it is corresponding to sharp reduction or sharp increase of your capacitance. Also, another one, let's consider this one, this horizontal part. Of course, if you wanted to have a lower capacitance, then the best way is just to separate your signal. Then instead of closely drawing your metal wires, then if you just draw your metal wires more relaxed way, then there will be significant reduction of capacitance. But what does it mean? It means that you just give up scaling. So since you wanted to introduce as many as capability into small area of your silicon chip, then you never cannot give up this distance. So there is a certain kind of constraint. So yes, so usually this width or spacing, these lateral ones, is really difficult to increase. So therefore what they do is just to make a play with this teeth thickness and the distance between layers to make an optimal value for these quantities, then without sacrificing the aerial efficiency, we can try to find a more or less optimized value for our interconnect. So that is typical way the technology guides that. Here we have one data from old technology like 180 nanometer technology, and here we have a M2. And yes, please have a look at this figure, but point is here we have isolated one and M1 M3 planes one. It means that we just consider one metal line, lonely metal line, and I mean that of course for this M2 level we have a certain neighboring wires. However, in the case of isolated case, we don't have any ones M3 and M1 level. Then what does it mean? These empty symbols just shows that the capacitance originated from the horizontal coupling. Yes, yes. And if we introduce here one metal plate and another metal plate, then what we will have is another coupling between M2 and M3 and M1 and M2. So the increased value here, field symbols, are originated from this horizontal contribution and this vertical contribution. So you can see that depending on the pattern, our capacitance can be highly affected. So if you have top and bottom layers filled with metal lines, then it can significantly increase your capacitance. By simply hand calculation, estimating this capacitance is not possible. So nowadays we must have certain computer programs to extract the capacitance. So because always we have well drawn the wire connectivity, because we are designers, then from this layout, then capacitance can be extracted automatically. Of course, for that purpose, we have to do two input. One is certain design, and another one is technology. I mean that even though we have the same design, if we just order this same design to one fab and another fab, since their metal wire realization or fabrication can be different, then they can give us different capacitance values. So we must consider these two things. Usually this technology thing is given from your fab guys. So as a designer, what you can do is just draw and see the result, and if that is too high for your performance or your purpose, then you can rework, redesign your long metal wires. Okay, so now let's go to this interconnect impact. I mean that here we have some examples. So in the textbook we have many examples. So I have just selected some examples to highlight the impact of interconnect. For example, let's say that consider a certain process. It has the copper wire, and the copper wire has the thickness of 220 nanometer. So now we have certain copper whose thickness is 0.22 micrometer. Then the first question is, if we have then what is the sheet resistance? You must remember that sheet resistance is given by the bulk resistivity divided by the thickness. If we have a thicker line, then sheet resistance is reduced. Then where can you find this bulk resistivity of copper? Yes, you have a book over this. So now you have copper value. So you can write down here. Oh, why do we have different numbers? So depending on this one, it can differ. So in this example, textbook example, we have used this value. So as you can see that even though this is material parameter, sometimes it can vary quite a lot. So please understand the situation. But anyway, for this case, they assume that this is the resistivity of our copper metal. Then now we have thickness. Then from this one, we can have this given value of sheet resistance. Simply speaking, if we draw, for example, length and width the same one, then that will give us 0.1 ohm. If we just make it twice longer, then it will become just 0.05. Oh, sorry about that. Longer, then we will have just 0.2 ohm. Instead of that, if we make this wire twice wider, 0.1 ohm once again, then these two resistors are connected in a parallel way. So obviously we will have the reduced value of overall resistance. So now let's assume that this let's assume that this typical metal wire has certain kind of a sheet resistance. Then once again, now we have 0.125 nanometer and extremely long line having 1 millimeter. What is the ratio between this width and length? This is between micrometer and millimeter. We have 1 to 1000, and between this value corresponding to 1/8 micrometer, we will have 1 to 8,000 the ratio between width and length. So we must multiply this number 8,000 into our sheet resistance. So we will have the resistance about 800 ohm. This is quite a huge number. So now let's say that we have such kind of a long line whose resistance is about 800 ohm. Then now we wanted to estimate the delay. So we have a long line, and at the end of this long line we have added a small inverter. So we have a long line, and at the end of this long line now we have a small inverter. And in order to drive this small inverter, whose size is just twice of a unit inverter, we introduce a relatively strong one, which is given by 10x times of a unit inverter. So if we don't have this metal wire, if we neglect this metal wire, then everything will be quite happy, because this is 10 and this is just number 2. So from the viewpoint of this 10 times wider inverter, this one is not a heavy load. So we can see that this is a quite easy problem. But now we introduce a very long 1 millimeter long line. So we wanted to consider whether our performance, delay performance, is affected by this introduction of a long line or not. Of course, we have resistance R of 800, but it's not sufficient, because we must consider the capacitance. How can we find the capacitance? Only with this kind of information we cannot estimate the capacitance. We have to certain specification about wire capacitance. That is given here. If you have 1 micrometer long line, then it will contribute 0.2 femtofarad. Why? It is given by the specification. And now we have 1 millimeter long one. So in terms of a micrometer, this is just 1000 micrometer. So overall capacitance will be 200 femtofarad. Okay. So now we understand from this simple calculation, the resistance of our long line is given as 800 ohm and capacitance is given as 200 femtofarad. So in the lumped element, we will just use this simple expression. So typically this one is given as called as pi model or whatever. So it is because here we have resistance and here we have capacitance, and capacitance, they are distributed. So since their shape just resemble that of Greek alphabet pi, so we call it the pi model. But anyway, then let's go to this pi model, and please note that here we have 100, so we just use half of it. Yes, now wire is done, and in order to calculate the Elmo delay, then we must consider the contribution from our inverters. So this is driver is given as 10 times the inverter, and we assume that N MOSFET has R equals 10K ohm. However, this is just a unit-sized one, and now we have 10 times wider inverter, so the resistance of our driver can be reduced by factor of 10. So we will have just 1 kilo ohm as a resistance of our driver. And here we have load inverter. This is 2 times the inverter, and what we can see is just input capacitance of our 2 times wider inverter. Since one MOSFET just to contribute to this 0.1 femtofarad, if we just consider 1:2 ratio between N MOSFET and P MOSFET, then we will have 0.2 femtofarad contributed from our P MOSFET. So are you with me? If we have a unit N MOSFET, then we will have just 0.1, and P MOSFET twice wider, then we will have 0.2. But all of them, the sum of them, 0.3 femtofarad, is corresponding to just a unit inverter. Here we have assumed that twice wider inverter, so we must do an additional factor number 2. Then we will have 0.6 femtofarad. Okay, now once we accept this kind of thing, then now here we have a driver, the signal is arrived here. Then let's say that, let's try to estimate the Elmo delay of what? Elmo delay of this node. The signal is applied at this node. Then what we have to calculate is the product between RC, but here we have intermediate root like that. Here we have one RC, and another RC. Here we have another RC. Also we have another RC that they can be just summarized in this form. So here we have one terms and another term, and point is, what is the contribution of our load inverter? Here we have certain numbers, quite a large number, but what is the real contribution from this 0.6 femtofarad? Among them, the contribution of this load capacitance, the requirement for filling our load cap, is simply given by 1.8 kilo ohm times 0.6 femtofarad. Then all other part, like 1 kilo ohm multiplied by 100 femtofarad, or 1.8 kilo ohm multiplied by 100 femtofarad, they are all related with this wire. So although in our previous consideration about delay in chapter 5, we just consider the input capacitance originated from the load. It was only because we assumed the case like driver and load are attached quite closely. However, if we have a long wire, then it can introduce significantly large amount of delay to our system. So we must be careful about that. And we have even worse consequence, like this kind of delay given by the product between R and C of our metal wires are quadratically increasing with the wire length. For example, up to now we have thought about 1 millimeter long line. It is a long line, but instead of that we are now considering twice longer line, 2 millimeter long line. Then what will happen? Since the length is twice, then maybe the delay is doubled. That's bad. But it's not the case. If you increase the length, then the resistance is scaled accordingly. Yes, we understand. Also, the capacitance is also doubled if we increase the length twice. So the product between R and C becomes not 2 times higher, but 4 times higher. That is the case. When the length is doubled, both of R and C are doubled. That is the case. So what will be the consequence? Of course, we must avoid a long line as much as possible. So if we can avoid the use of a long metal wire, then we can significantly reduce the delay by this metal wire. And instead, this is important one. And here we have some simple manipulation. So we have, for example, many different ways to consider this R and C, this distributed R and C. For example, if we have a long line, then we can consider a short segment, and it can be sometimes modeled as this way, R, C, and sometimes it can be also modeled as R, C, or sometimes it can be modeled as R, and C. So there are many different ways to model this short segment. So maybe you think that then is there any difference due to this different ways of consideration? But please think about this. Although this one can have different shapes, but when we just concatenate them, then eventually we will have this form. Yes, this is the consequence of your L model. Are you with me? Then if you consider your so-called T model, then what will happen? In this case, if you just add this T shape once again, you will have this kind of behavior here. So are you with me? So simply here you have serially connected resistances here and there. They can be equivalently modeled. Modeled as what? Yes, it is once again R, and it can be also R. So if we select this one single resistance as half R, then we can recover anyway the same form of R and C. Same happens to our what? Same happens to our pi model. So please try to do that. So now let's go to our final slide in this today's lecture. Up to now we have thought about the delay, but how about the energy consumption? So since we have a capacitor inside our metal, so now say that RC, this is a long line. Then now let's say that we just, this is the input part, and we just increase the value, signal value from 0 to VDD. Let's assume that originally all over our output value or voltage was 0. Then what will happen? When we increase this value, then yes, after certain time delay, then it will be just VDD. After that, also it will be increased, and it will be increased to VDD. So after long time has passed, then every small capacitance, distributed capacitances, will be charged with VDD voltage difference. So simply speaking, in order to charge this small c, let's say that this is small c, then you must spend, yes, the energy like the c charge and discharge, then you must spend something like this, c times square of VDD. So now it is obvious that this slide. Long wires have significant capacitance. So in order to charge and discharge these capacitances, then we must spend energy. So now let's have a look at we have used a long line, so it has capacitance 1 millimeter long line, and it has 0.2 so it has 200 femtofarad of capacitance per 1 millimeter. If we have this 200 femtofarad, and if our VDD is given as 1 volt, then simply speaking, in order to charge and discharge this overall capacitance, we need this kind of calculation: 200 femtofarad times 1 volt square. That is the amount of energy which requires to one single cycle. So you will have, yes, this is corresponding to just 0.2 picojoule, or in the same way 200 femtojoule. So that is quite obvious. And now let's think about twice longer metal wire. Yes, 2 millimeter. Then what will happen? In this case, of course, we have twice larger capacitance. So you can see that for this technology, we spend 0.2 picojoule per 1 bit switching. 1 bit means that 0 to 1 and 1 to 0. So in order to send something, 1 unit signal, then we must spend 0.2 picojoule. But when we have on 1 millimeter long signal, if we have, for example, 2 millimeter long signal, obviously our energy consumption just becomes 0.4 picojoule instead of 0.2 picojoule. That is quite easy. However, in this last line, we have a little bit different view. Okay, this one, just this 0.2, just says that in order to up and down a signal, then we need one single operation just require 0.2 picojoule. Yes, we can understand. But what happens if we switch it, or if we send 1 billion bit per second? Then what happens? This single operation just spend 0.2 picojoule. However, in order to send our signal, we just introduce many of these switching levels. Then what will happen? Per 1 second, we must repeat this kind of job 1 billion times. So simply speaking, we must multiply 10 to the 9 to this number. Please note that this pico is corresponding to 10 to the minus 12. So you can easily understand this one is given by 0.2 millijoule. Okay, is spent by what? Spent by this 1 second period. So 1 second and certain energy dissipation that can be written as this power unit. So you can say that this one is corresponding to 0.2 milliwatt consumption. So of course, this is all related with our assumption. If we send our signal with 10 to the 9 bit per second, then it will consume 0.2 milliwatt. For example, instead of that, I just reduce my bit rate. Instead of 10 to the 9, I just reduced it 100 megabit, so 10 times smaller. Then what will happen? So in this case, it will just spend not 0.2 milliwatt, and it will just consume 0.02 milliwatt for this 100 megabps operation condition. So simply speaking, if you wanted to increase the operational frequency or bit per second, bit rate of your metal wire, then you just increase the energy consumption of your metal wire. So everything just spend the energy. If you just wanted to make it quicker and faster, then you must pay something. Here your pay, your cost is energy. Okay, so although we have 10 more minutes, but I wanted to wrap up today's lecture because we must discuss about our final lecture, our final examination schedule. Okay, thank you for your attention. Okay, so have you thought about